In this lesson, we're going to be looking at inverses of functions and relations. So our topics today are going to be inverses of relations, then we're going to look at inverse of functions and the horizontal line test, and then finding inverse function formulas. So first, let's look at what makes a relation and its inverse. So we're going to look at our relation R, and again, a relation is just a set of ordered pairs that we denote or name by a capital letter. The inverse of R, of this relation, is denoted by R to the negative first power. And if we have a relation, here it says that I have AB is in my relation R, that ordered pair, then its inverse is going to have the point B comma A. So all this is saying is if I have a relation that has the points 1, 2, 2 comma 3, and say 3 comma 4, then its inverse is going to have the points 2 comma 1. All I'm doing is switching the x and the y values, 3 comma 2 and 4 comma 3. So I have my relation, and then to find my inverse, all I have to do is switch the order of the x and the y's of the ordered pair. So let's look at an example together. Determine the inverse of the following relations, then graph each relation and its inverse, and determine the domain and the range of both. So let's look at A first. Here, if R has the points 4, -1, -3, 2, and 0, 5, then its inverse is going to contain the points -1, 4, and again, all I did was switch the x and the y values, 2, -3, and 5, 0. Okay, so let's talk really quick about, are these relations actual functions? Now remember, in order for something to be a function, every input has to have exactly one output. So every x value has to have its own unique y value. So if we look at R here, is this a function? Okay, so 4, -3, 0, none of my x values repeat. They have all unique y values, so this is a function. And then what about my inverse? Is it a function? Okay, same thing applies here. Does every input have exactly one output? Yes, all of my x values have a unique y value, so this is also a function. Okay, we're going to look at B in just a second on the graph. And we're going to look at A on the graph too, but then it says determine the domain and the range of both. So still looking at A. Okay, my domain, remember, is all of my x values. And remember, my range is my y values. So here in this same problem, in relation R, my domain was 4, -3, 0, and my range was -1, 2, and 5. Okay, so what about my inverse relation? My domain would then be actually my range from the relation, so it would be -1, 2, and 5. And then the range of this inverse would actually be what was the domain of the original relation, which is 4, -3, and 0. Okay, and now let's look at it on the graph. So if we look here in purple is my original relation. Okay, here I have the point -3, 2. I have 0, 5, and I have 4, -1. That's my original relation. And then to get my other points, the green points are its inverse points. So here at the -3, 2, it changed to 2, -3, which is down here. Okay, then I had the point 0, 5, which changed to 5, 0, which is over here, making them bigger. And then I had the 0.4, negative 1, which changed to negative 1, 4, which is up here. So I can graph, if I have the graph of a relation, I can still easily find the inverse points just by taking and swapping the x and the y values. Okay, what about my y equals x squared? Okay, that was the second problem. So my original relation, y equals x squared, well, its inverse, just like we did with the ordered pairs, we switched the x and the y's. So to find its inverse, if you look, the y in the equation became the x, and the x in the equation became the y. So my inverse relation here is actually x equals y squared. And we're going to use this concept in just a little bit. So for y equals x squared, we know that it looks like a parabola. I'm going to kind of jump ahead. Here in the graph on the purple, that is our parent function, y equals x squared. We remember that our vertex is here at 0, 0. We have a nice parabola here. So that's what our graph looks like. Its domain, remember, is all the x values. So as I keep going to the right and as I keep going to the left, I'm going from negative infinity to positive infinity. And then my range, though, starts at 0 and it goes up to positive infinity. So again, here, my domain is all real numbers, and my range of my original relation goes from 0 to positive infinity. Now, even though I don't know what the graph of my inverse necessarily looks like right now, I can very easily rewrite the domain and the range. So all I know is that this domain here, it is exactly the same as the range of the original relation, and the range then is exactly the same as the domain of the original relation. So my domain goes now from 0 to infinity. So that means that my x values are only going to be positive numbers, but my range on my y scale, I can go from all negative numbers to all positive numbers. And if we look at the graph, it's over here in the green. Okay, I have on my domain all here. I start at 0 and then my x values can go to infinity, but then my y values are all real numbers, negatives and positives. Now if you look at the graph, note that the graph of both of these, it's just been turned, but essentially it has the same shape. The inverse and the relation does, so keep that in mind. So some things that people get confused from with the notation here, f to the negative first power, okay, does not, a lot of times when you see a number like 4 to the negative first, that tells us actually to move it to the denominator because we can't keep that negative exponent, so that would be 1/4. Well, that's not what's happening here with a function. Okay, so f to the negative first does not mean 1 over my function. Okay, the only time that we take the reciprocal is when we are dealing with numbers or an expression. When we're dealing with equations or functions, the negative first power is all that's telling us is that we are looking at the inverse, not the reciprocal. So make sure you don't get that notation confused. Now, I know everyone in here has heard of the vertical line test. Okay, remember the vertical line test told us if something was a function or not. The graph. Okay, which means if I had the graph of the equation, if I drew any vertical line and it only touched my graph in one specific place at any time, then it was a function. Well, we do have something called the horizontal line test. Now, the horizontal line test, it says that if my graph f passes the horizontal line test, which means if I draw a horizontal line through my graph, if every horizontal line in the plane intersects the graph no more than once, if f passes the horizontal line test, then this inverse is also a function. So if I have a function, if it passes the vertical line test, which means that I only hit that function, that graph, in one spot at any time, then its inverse is also a function. And this is what I just talked about with one-to-one functions. That is the vertical line test. So let's look at example 2 here. Determine if the following functions have inverse functions. So we're going to look at the graph to see if it has inverse functions or not. So f of x equals the absolute value. Remember, these bars here are absolute value bars. Okay, so does it have a function? So let's go and look at its graph really quick. This is what the graph of the absolute value of x looks like. So does it pass the vertical line test? Well, it hits it right here and it hits it right here. Since it hits it twice, then its inverse is not a function. Okay, it does not have an inverse function here, since it does not pass that vertical line test. Okay, if I go back to b, g of x equals x plus 2 all to the third power. Remember, this is a cubic function. Okay, which looks something like this on a graph. Remember this plus 2 then, if you remember your shifts, this plus 2 moves it left 2 spaces. So let's look at it on the graph. I got it here on the graph. So if I draw a horizontal line anywhere through, you see we've got one drawn right here. It only hits in how many spots? Just one. Have a horizontal line here. How many spots does it hit my graph in? Just one. And I have a horizontal line here. I can keep drawing them. This one only hits in one spot. This does pass the vertical line test. So since it passes my vertical line test, that means that I do have a inverse function. This original function has a inverse function, and we can find it, and that's what we're about to talk about. So algebraically, any two distinct elements of the domain of G lead to different values when plugged into G, so G is one-to-one and hence has an inverse function. Okay, if I'm given a function, how can I find its inverse? There are several steps. Step 1. I'm going to replace my f of x or my y value, okay, with x. And then I'm going to exchange my x value with y. That is step 2. So wherever I have an f of x, first I'm going to put y in its spot. Because remember, f of x and y are exactly the same thing. They can be used interchangeably. Then everywhere I see an x, I'm going to change it to y. Everywhere I see a y, I change it to x. That's because if I have a relation, so set of ordered pairs x comma y, to find this inverse, I switch the x and the y value to get the new ordered pair. So we're going to do that inside of the equation. Step 3 then, I'm going to take that new equation when I switch the x's and the y's, and I'm going to solve that equation for y. And then at the very end, I'm going to take the y out, and I'm going to replace it with my inverse notation, f negative 1 of x. So We're going to look at some together here. So I've got two functions. The first one is f of x equals x minus 1 to the third plus 2. We're going to look at that one first. Okay, so let me rewrite it really quick. It was f of x equals x minus 1 to the third plus 2. Okay, very first step. I'm going to take the f of the x out, and I'm going to replace it with y. So I'm going to get y equals x minus 1 to the third plus 2. Okay, so my first thing I did was replace f of x with y. That was my first step. Second step, everywhere there's a y, it's going to turn to a x, and everywhere there was an x, it's going to turn into a y. So my new equation now is going to look like x equals y minus 1 to the third plus 2. Switch. So all there is switch x and y. Okay. My next step is I need to solve for y, which means I need to get this y right here all by itself. Okay. So it's just kind of like rewriting order of operations, moving things over. I gotta get the y all by itself. So the first thing I'm going to do is subtract the 2 over. I'm going to have x minus 2, put in parentheses because they're together now, equals y minus 1 to the third power. Now I still got to get the y by itself. Still is not by itself. I cannot just add the 1 over because it is bounded by this to the third power. So how do I get rid of to the third power? Okay, the inverse or the opposite of raising something to the third power is taking the third root of it, or the cube root of it. So I'm going to take the cube root of this side, do that in another color, the cube root of this side, and if I do it to one side, I have to do it to the other side. So we're going to get the cube root of x minus 2 equals, now the cube root and the third power just cancel each other out and leave me with y minus 1. I'm getting closer just having the y by itself. So I need to move this minus 1 over, and I am going to do that by adding it over. I'm running out of room. So I'm going to get the cube root of x minus 2. Now when I add the 1 over, it does not add to that minus 2 inside of the radical because all of that's inside of the radical here. I'm going to put plus 1 outside of the radical equals y. This is my new function. Now to show that it is my new function, my inverse function, I now have to take the y and replace it with the inverse notation. F negative 1 of x equals the cube root of x minus 2 plus 1. And then this now is my inverse function. Okay, let's look at b together. b was g of x equals x minus 3 over 2x plus 1. Okay, first step. I'm going to take out the g of x and I'm going to replace it with y. y equals x minus 3 over 2x plus 1. Next thing I have to do is switch. All the y's become x's, all the x's become y's. So I'm going to do that. X equals y minus 3 over 2y plus 1. Okay, now I've got to get the y's by itself. In order to do that, I can't keep that denominator. Okay, so in order to get rid of this denominator of the 2y plus 1, I'm going to take and I'm going to multiply both sides by that denominator, 2y plus 1, which makes those cancel. And then I got to do it to this side, multiply it by 2y plus 1. Okay, and then at that point, I now have x times 2y plus 1 equals y minus 3. So you see this right-hand side here of this equation is getting a little bit smaller where I can get the y all by itself. But before I get the y all by itself, I'm going to actually take this x and I'm going to distribute it in, which is going to give me 2xy plus x equals y minus 3. Okay. Okay, we now have to solve the equation for y. So I want to get everything that's alike on one side. So I want to get my y's together. So I'm going to kind of do something different. I'm going to take this y over here, and I'm going to actually move it over to this side. And then I'll move the x over to this side so I get like terms together. So I'm going to subtract the x over, and then I'm going to subtract the y over. And I'm going to do all that here in this one step. So bear with me. So I am now going to have 2xy minus y equals negative x minus 3. And I did that because now over here they have something in common. They have a y, so I can factor out that y. And I'm left with 2x minus 1 equals negative x minus 3. And the y in this 2x minus 1, so I'm trying to get this y right here all by itself. Since these are being multiplied, to move the 2x minus 1 over, I have to divide by it. That gets it rid of over there, and I can divide by it over here. And now I have y equals negative x minus 3 over 2x minus 1. I have solved for the y. It's all by itself, and I need to do one more thing. I need to show that this is the inverse function, and we are using g as our function. So it's going to be g of negative 1 of x equals negative x minus 3 over 2x minus 1. There is my inverse function. Okay, I'm going to stop right here for today. Tomorrow I'm going to add the very last part of this lesson, and it's just how, if I know my function and if I know my inverse function, how can I, or if I know two functions, how can I determine or prove that one is the inverse of the other? So tomorrow there will be a short little video. Please go ahead and log on to HawksLink. I have put the directions on how to do that on your Canvas under announcements. There's some short little videos of how to get onto HawksLink. You will need once you get onto HawksLink, or Hawks Learning, sorry, you will need that access code from your book that was supposed to be emailed to you. So make sure, watch this video tonight, take notes on it, make sure you can get into Hawks Learning. I'm going to post the very last part of the notes tomorrow morning, and then you will be able to complete your assignment.